So yeah, let me just give you a kind of short introduction why we are having this this workshop, because we actually believe that AI can help with respect to early warning, climate risk mitigation, but it can, it doesn't mean it does. And so we need to actually discuss jointly together what are the opportunities, but what are also the challenges. We look at the standard framework, key recommendations. I think most of you are aware of those. There's exactly one of the central pillars is by developing multi-hazard early warning system, develop integrated information systems, and also evolve traditional risk assessment, whatever that means, and also have new ways of communicating risk. And you will see, we will argue that AI can play a role in all of those pillars. WMO presents that this is 4 pillars of early warning systems, which makes a lot of sense. Is a very good multi-hazard early warning system approach. But if you look into the document, you can have the impression that actually there are gaps. There are gaps related on the one hand to the use of artificial intelligence, but also it's a bit centered on the atmosphere and climate and weather. So there are gaps on ecosystem and societal vulnerability and also systemic impacts and risk. And we want to contribute to this, to overcoming this. If you look at the early warning chain, you have seen the book, The Perfect Weather Warning from Brian Golding, from High Weather. And we redrew his figure and modified it a bit. So we really have to embrace a whole early warning chain from observation to decision. And let's walk through that. Starting, of course, with observing, with modeling. There has been a lot of breakthroughs with AI on atmospheric models, where one has been training on reanalysis data. One of the models has been also mentioned yesterday several times by DeepMind, GraphCast, but it's only one of them. And the point is that these models are super fast. They can emulate the cloud models very well and are even arriving at better performance when they are trained against quasi observations or reanalysis data. So that's something where I already plays a very important role. Let's move on to the hazard and impact forecast. That's important. I mean, that's important for the people, of course. It's not just the weather. It is what happens to the landscape, to the ecosystems, to the society and economy, and to the lives of people. There, of course, we have this classical risk model that is already in the earlier version of the IPCC, where we need to understand that risk is not equal to hazard, but risk is kind of a function and a combination of the hazard, the exposure, if people are living where the hazard is happening, and the vulnerability of people, which depends a lot on societal and socioeconomic conditions. This is a good view, but it also ignores that we have interactions between the different domains, if you want. And so I think the paper by Simpson, and this has been also adopted by IPCC, more or less, shows actually we need to think a little bit more complex. On the one hand, we need to add one risk factor, that is actually the response of users. Yeah, I can sit here, I will just. Response as a risk factor, and then the interactions between the domains causing cascading compound risk that you can then also see in different ways on the right hand side. Now, let me give you one example that we have been studying some aspects on, and also other people. That's the heat waves that hit Russia back in 2010. So it's quite well studied. So everything started from a blocking high on top of climate change, causing an unprecedented heat wave and drought that stressed the ecosystems, the vegetation a lot, vegetation desiccated, leading to forest fires. And the forest fires, of course, pollute the air with nitrous oxide, with fine particles. And what is really important here, and this is true for the Russian heat wave, but it also has been shown for Australia, has been shown for California fires, that only the synergy between the heat wave that stresses organisms and the air pollution actually cause these high strain on the health systems and the mortality of more than 10,000 people. And then, of course, also the economic systems are stressed from the agricultural side. For example, we had a lot of crop failure, and if breadbasket is hit by such an extreme like the wheat production in Russia, there were clearly links to high volatility of wheat prices. And there are more and more studies showing that at least this kind of volatility and this kind of economic impact then also was a risk multiplying factor for social unrest, for something that we now call the Arab Spring. So it is really, if we talk about this and talk about climate impact, we really need to consider that the different sustainable development goals are interconnected, and we need to look at these. In Germany, we learned also that lesson that just looking at weather is not enough. We had these mega floods in Rhineland and other areas with more than 100 people dying, more than 10 billion, and the highest since the Second World War damage that we experienced in Germany. What less people know is okay, that was of course caused by a strong rain event, so not big event, was much more than really the rain over a short time. But what less people know is that a very similar meteorological event happened a couple of months before in Mecklenburg-Pomerania here in northeastern Germany, and almost nothing happened. So nobody died, very little damages. It was not even in the news, really. And why is that? Because the landscapes are different. Here we have loamy soils, denser soils, hilly terrain, while in eastern Germany we have gentle terrain and sandy soil. So in eastern Germany, actually, all the rain can be absorbed by the soil, and actually it's good because it recharges the groundwater. So same weather, very different impact. This basically means we really need to adopt a system view when we look at climate impacts, where we have interactions between the atmosphere, the biosphere, and the anthroposphere, also cascading impacts with, inside them, and then of course we also need to consider. And this is of course a very complex system at the end, and it's very hard to model that with one physical equation or several physical equations, and that's why it's really important to have observations. Yeah. And that's also where artificial intelligence comes in to understand this complexity better. What is also quite important, we're talking about different time scales, different spatial scales. We also talk about humans, so perception, valuation, and beliefs play a role if you think about responses. One example that goes in this direction, there are others, is basically that we can actually see that also weather extremes have very contrasting impacts on different systems, like what the vegetation is doing, what are the crop yields. So these are quite well correlated. But if you talk human mortality or property damage, then actually other extremes play a more important role. And one thing that we also looked at was attention, and this goes into this kind of perception problem. It's really interesting that attention is really different from impact, where these kind of drastic extremes like floods and storms get really a lot of attention. And the attention is actually larger than the impact sometimes, while things like drought and these silent killers actually really don't receive the attention that they should get. So yeah, coming to the last part of the communication, also there, AI can probably play a role. If you go back to, for example, the German case of the Ahrtal flood, if we get a warning, 200 millimeter of rain or 8 meter of water, it's very abstract, and many people cannot digest this information, but particularly if it's unprecedented. So we can use artificial intelligence to imagine a world with some extremes. Here, for example, how landscapes change. This is more a climate perspective with temperature and annual precipitation. So at least it gives some plausible futures in this context. But more importantly, concrete examples of a flood can be estimated with creating a map where really inundation is happening. And even with generative approaches, one can even create photorealistic images that basically show the people how their property look like. And the idea is basically that it's a much more intuitive warning that will hopefully be much more actionable for response, both for people but also for decision makers. Yeah, and of course, chatbots also can play an important role, so because it can be interactive and engaging. Okay, some final thoughts and challenges. I think one thing is actually interesting. I mean, there is progress with respect to preparedness. So just for example, look at report death by decade is going down because people have managed to prepare. But what is also was quite interesting and very nicely shown in that study is that as soon as an event is unprecedented, suddenly the preparedness doesn't work anymore. So we are really not prepared for unprecedented events. It comes up again and again. So that's certainly a thing that one should discuss and address. Another important point one should discuss is a different timescale that's very nicely shown here in this report, where of course at different timescales we have different planning horizons, and what we actually think that is of course important is the short-term anticipatory action, which is, let's say, happens within a year, but also something that's going beyond years towards decades, which allows actually for more strategic planning. Changing infrastructure should be also part of early warning thinking. Last but not least, another challenge, of course, is that not the impact is not always where the hazard is happening. Easy example are river systems where the flood waves kind of transported across boundaries. So nature doesn't know political boundaries, and so this transboundary climate risk is also a very, very important aspect, and of course then governance plays an important role. And last but not least, one important aspect of early warning that needs to be addressed is really the inclusivity at different levels, different types of inclusivity: sex, gender, age, race, abilities, religion, precarity. So this is really important when thinking about also leaving no one behind. And this is, I think, that can be a critical discussion. Can actually I help or not? I think this kind of discussion one should also have, and I guess people have that partly addressed, but also make the point, think about it, I think, during the discussions. And so I'm looking forward to the talks and the presentation. Thank you. So, and I will actually moderate the session because they didn't think about it. I don't know if there are any questions regarding my intro or comments. Certainly welcome. Yeah, we have two so in the back. Oh, we have three, and then what are you?
Thank you. If you can, sorry, Muhi Usama from WMO. If you can display your slides on the four components of early warning system.
Yeah.
And thanks for quoting WMO's work in it. I think it's very nice to see that our work is seen and valued. It's very interesting outlook that the view that you see in these four pillars of early warning system, and then you clearly identify the main gap, which is artificial intelligence. I think this is the future that we are discussing, especially in the early warning for all.
Yes.
And we are still finding forms, actually. We do have UN's subgroup for artificial intelligence for early warning systems. So it's really good that you write that and you mentioned that. It's one of the key components of the early warning system, which I think we will have to revise with the inclusion of artificial intelligence on that. So my comments is to thank you for that, and also to call for any ideas from the rooms. If you wanted to do research on artificial intelligence of these 4 pillars of early warning systems, I think we'll be happy to collaborate. Disaster risk knowledge is led by UNDRR, ITU with the communications and preparedness and response with IFRC, but we have to also mention the work of UNDP that works in the country. We work together actually in the rolling out of the early warning systems for all. Yeah, thank you.
Yeah, thank you. Actually, yesterday we talked to Elena Babi also. So yeah, I think we should make the link more strongly.
Yeah, I was just wondering, because I've done work with like the Red Cross and their early warning systems and anticipatory action, and like sometimes I've like questioned whether it's like actually cost effective, because we're spending a lot of money like on research and development to build these models that can like make like super accurate predictions, but like there's still maybe like the machine learning is like marginally or like only a little bit more accurate than like a more simple model. And then like on the ground, I'm still not convinced that it's like affecting decisions that much. Like even if we're providing the models to stakeholders on the ground, the things that we're modeling like from a like maybe like academic lens or like a less like on the ground lens don't necessarily map to what they're using. If we're modeling like damage to houses, maybe they care about like damage to like fishing boats or something, which like we can't even track. So I don't know, is it just like if you could give maybe your take on like how cost effective you think this is? Like could the money be better spent on just like aid for disaster relief?
Yeah, I mean, I think you're not referring to the general principle of anticipatory action.
Yeah.
You're not. I mean, that is, I think, quite clear that this is cost effective.
Yeah.
But you're talking about only about the AI part. No, and I would say at the moment, one issue is if the AI is only considering weather, maybe then it's marginal, although the speed up is not marginal, so much more. But if you consider the impact, and that's exactly what you have been talking about, the diverse impact that can happen, and where the amounts are hard to make. If you are able to make very fine-grained effects and basically forecast them, I think then it will be can be quite important, quite a game changer. But yeah, we are not there. So that's why also research is needed. On the back.
Thanks, Marcus, for the presentation. I mean, as you rightly mentioned, that it could be used for every single value chain of the AI could be utilized. Do you have an example how AI has been used for generating some hyperlocal information at a community scale to supporting early warning system?
Yet, not yet, I think. Oh, do we? I mean, maybe you have.
I'm just
no. I think this is, but this is exactly the point. So this is kind of a call for thinking that in that direction, and for discussing how it can be done with specific use cases. The last comment, I think that we did move on.
Just about that, I heard that the WFP has a map. I think it's called Sky, where they're displaying live satellite data after disasters. So it would be hyperlocal, showing specific buildons, the amount of damage.
Okay, that's kind of
some things
post
like
disaster.
Yeah.
There's a lot of that going on, but I think it was more referring to the forecast.
I see.
But yeah, but one should learn also from that. Certainly, disaster response. But we can learn how local stuff can be integrated for preparedness. Okay, we should move on. And we have the next presentation by Julia Martini from the World Food Program.
Oh, because I want to. I haven't got enough.
Okay, so good morning and thanks for being here. So I will not talk actually directly about climate risk mitigation, but more about an application that would benefit from any warning system related to climate and of course climate risk mitigation. So let me start introducing WFP for who is not familiar with the organization. WFP is one of the UN agencies and it's the world's largest humanitarian organization. The main goal of WFP is to reach zero hunger by 2030. WFP is funded entirely by governments, companies, and private individuals, and we operate in emergencies. So in context with high variability and high complexity. Just to give you a feeling of the complexity where WFP operates in 123 countries. We are more than 23,000 employees. We collaborate with almost 1,500 partners. And in 2023, we reached and we assisted 152 million of people. 152 million of people is actually less than half of the people that were actually in need of assistance. And as you can see from this graph, the gap between the people in need and the people that actually receive assistance is just widening. This number is actually quite worrying if you think about the goal of reaching zero hunger by 2030, and it's even more worrying if we look at the funding that WFP is receiving. So we can see that the contributions are not keeping pace with the needs, and between 2022 and 2023, the funding gap extremely widened, moving from a 34% funding gap to 64% funding gap to last year. So I think looking at this information, with the information before about the difference between the people in need and the people that receive assistance is, I think, obvious to ask ourselves, how can we reach our goal of zero hunger when we don't have enough resources? We need to do more with less. And so we need to leverage technology and to reduce waste, to try to gain wherever there is a margin. So of course, in WFP operations and where we work, there's a lot of margin in different areas. And one of these areas is actually the supply chain planning. When we talk about supply chain planning for WFP, we can consider two parts. One is the upstream planning and one is the downstream planning. When we talk, for this presentation, I will focus on the optimization of the upstream planning. When we talk about upstream planning, we talk about the supply chain from the supplier to the recipient country. So when the good move between where we buy it, the supply from where we buy it, and all the steps until it's received in the country, but not within the country. So to do planning in this leg, we need to answer a series of questions. So first of all, of course, we need to know what is the demand that we need to fulfill for every country at every month, for every month. And what do we need? So what do we need to procure? What's the quantity? How often we can procure, from where? And then of course there is so many other questions. So for example, which lanes, which route will the good take? So where is there any sourcing constraint? So as you can see, there is a high level of complexity. And to solve this, we require a lot of sub-activities. So we need to do demand planning. We need to understand what are the prices of the various goods, what are the capacities of hubs, transportation, and then we need a sourcing strategy, an inventory strategy, a delivery network, where of course climate becomes important, upstream and transport forecast planning, and then of course we need to be able to do a performance analysis. So as you can see, I can understand the upstream planning is hard because we need so many things. So without listing all of them, you can already understand the complexity. And the classic planning was done in Excel. So that's something that I would say we cannot do anymore, considering also the technology that we can use and we have and we can leverage. And in particular, I want to highlight the unpredictability, but also the variability for all these components where we have, because we have sourcing and donor constraints, we have a risk of supply defaults, potential supply network disruption because of climate, because of conflicts. So how can we reach a good quality decision with so much variability and uncertainty? So our idea is to leverage technology and use actually this variability and uncertainty as input to feed an optimization model and analytics to being able to have a good plan and to perform informed decisions. So actually what we propose concretely is to create a sourcing and delivery plan. So a 12-month plan that provides recommendation on the upstream supply chain plan that takes into account the demand plan and the risk strategy, the supply chain strategy, inputs and constraints, and of course takes into account the uncertainty of the demand and the supply. We have 4 key elements of this process. So we need to have a supply network utilization, planned utilization, which is based on the logistics constraint and inventory strategy. So where things can travel from and to, stopping where, what is the availability of hubs where to stock things, a list of proposed purchases and stock movements, because of course we have a high complexity. As I mentioned last year, WFP provides support in I think 78 countries, and so I mean of course the complexity is high, and we have a projected coverage of the demand and inventory levels, and in the end we can also have unexpected utilization of different suppliers, corridors, and various other things. So at the end we want to know what to buy, in what quantity, where to buy from, when it's the best moment to buy, how to transport it, how to store it, and how to deliver it to operate efficiently. We expect to, from this approach, we expect to have multiple benefits. First, of course, an optimized planning decision that accounts for all this variability and all the inputs, and most of all, increase the resilience to unforeseen changes in the operating environment that can be due again from two different. The unforeseen changes can be also due, for example, to conflict or just extreme weather events. With this approach, we have a medium and long-term visibility on expected coverage, shortfalls, and sourcing plan. And we are also able to buy at the right time, enabling a steady flow of supply, so to avoid any interruption of the pipeline. So our solution is called Scout, and it's a system that helps to optimize where to strategically store commodities, so when to look for the food, and how to use and best use our limited resources. So we want to avoid to have a fragmented process. We want a unique, coherent, and consolidated process that sees WFP operations as a whole, or at least at the regional level as a whole, and it mitigates the risk of silos decisions, which also lead to inconsistencies and also not optimal decisions. So our idea is to consolidate together information about demand, about the network, about the supply, to have as a result our sourcing and delivery plan. We need to formulate the problem, of course, in a mathematical way. It's an optimization problem, and we have multiple things that we want to optimize. So we want to maximize coverage, which is actually our primary goal. So we want that the country receive at the right time what they need. But we, of course, also want to minimize the cost, minimize the travel time, and maximizing the sustainability and maximizing the robustness. All these as a series of constraints, starting from supply capacity, storage limits, transport capacity, and of course, budget and sourcing constraints. So what we aim at solving is a temporal network flow linear program problem, where the coverage in our objective function, we have kind of infinite high
Ladies and gentlemen, head on over to the center stage in room A on the ground floor to see inspiring and informative keynotes and hear how companies like MasterCard and 3M are using AI for good, and see how technology like AI-powered exoskeletons can empower people with disabilities and change the future of mobility. See you soon.
So,
Stay here.
So we have a objective function. It is a linear combination of all our objectives. So we assign an infinitely high coefficient to the coverage, and then other coefficient for our secondary objective that we can tweak. So for the cost, the time, for example, CO2 emission. And then all of these are subjected to some constraint, as I mentioned before, the supplier capacity, storage limits, and so on. And we can see the problem as a graph where we start from suppliers, we have hubs, and then the receiving countries, and we have the time discretized where at each month, for each commodity or each group, we know from where to where they move and in which quantity. So just to give you a bit more detail about how Scout works, we start from all this information that usually come from system data, so all the information I mentioned before, and then through a web interface, we can create scenarios. So we can create all different possibilities, assign different coefficients to our components of the objective functions. And at this point, we have a first step where we need to make the problem actually solvable from our optimization engine, using, for example, and also to make it solvable in a simpler way. So we use graph algorithms to prune the search space. At this point, we finally solve the optimization problem. And then we recreate the solution in a coherent way, where for each specific order, we have an optimized route, and we can also detail from where we buy, so the supplier, with the recipient, what's the transport mode, and also what's the transfer. Now, at this point, we can navigate the solution through our web interface. So we have our source and delivery plan. And thanks to the entire infrastructure, we can create multiple scenarios, compare the results, and then decide with our stakeholders, so our colleagues that work in the regional bureaus and the country office, what's the best solution to adopt. I will present also a use case. So we piloted Scout since last year for the region of Western and Central Africa. It is a very complex region where WFP operates in 19 countries. We have low availability of goods and high prices and high operational needs during the lean season. It goes between June and August, at least so far. We have a volatile geopolitical context. We have access constraints. And also it's important to notice something that I didn't know before joining the team is that out of these 19 countries where WFP operates has actually trade restrictions, so things cannot move between certain countries. So when we do our supply chain plan and we want to move things between countries, we need to consider also these constraints. And of course, there is also a high uncertainty needs and also the expected funding. So we started running a pilot in 2023 for this region with the goal of serving WFP needs and the region needs to avoid pipeline breaks. And we wanted, of course, foster local and regional markets, so to also increase the sustainability of the process. Of course, we want to buy a lower cost and we want to avoid overstock. So through an iterative process, keeping in mind this objective, we could build different scenarios where you can play with your different inputs and also putting constraint. For example, you could put any constraint due to pipeline interruption, do, for example, any climate extreme weather event that at the moment you don't foresee. But if you have, for example, a early warning system, you might take into account considering the likelihood of this event. And then we could, after building the scenarios and obtaining the different results, we could analyze all these different results. And it's also interesting that previously any plan was taking an average of 5 days to be built, and with this tool, the time was reduced to half a day. So it's a huge saving in time, and with also obtaining analysis with a better level of detail. And then we could check if our objectives are met. If not, we continue again to building scenarios. We have some very interesting expected benefits. So profiting from the harvest season, so doing procurement of local and regional commodities during the harvest season. So without waiting the lean season where the demand is higher to procure internationally, we could see that we would have 4.7 months of forecasted demand met for the lean season in 2024. Of course, this number needs to be confirmed at the end of the lean season. Compared to the previous number, it was only 2.7 months covered. And even more interesting is that the approach resulted in a projected cost avoidance of $4.5 million during the 2024 lean season, via local prepositioning of sorghum and beans. So if we buy sorghum and beans locally, just in advance, we can save a huge amount of money. Next steps, we of course are still in a phase of development of the tool, and we want to add information and variables. So of course we want to productionalize Scout version 1.0. We first had just a pilot. We want to do testing and roll out to other regional bureaus and country office in WFP. Capacity building, we want to enable the planners in the regional bureaus and country office to be able to use the tool independently, play with it, and analyze the results. We look, of course, for partnership and collaboration. So if you have something, you're working on something where we could work together, we'd be happy to hear it. And we are particularly interested in addition of new features. So one is improving the demand plan, and one is a stochastic approach of the optimization. And looking a bit more in detail about these two topics. So we would like to move from a classical time series forecast to machine learning, where we don't just use the past demand forecast and past purchases, but we also would like to include information regarding funding, regarding climate, regarding food security forecast. So to have a demand forecast that is more informed and could better feed our optimization model. And in all of this, given the high uncertainty of all our power goals, we want to insert the uncertainty quantification and move from a deterministic to stochastic optimization process. So to add a robustness layer to our tool in order to make a decision which takes into account all the possibilities and from there takes the one that has the lowest risk. Thank you.
Got those besides the questions. Otherwise, okay, yeah.
Yeah, I just wanted excellent presentation. Thank you so much. It really gave me a really bigger insight as to why WFP won the Nobel Prize just years ago, right?
Yeah.
This thing that you want to add, how long will it take, and why is it complicated? Like, is it something that now that you've done one portion of it, it will come on faster than the first round?
You mean these two parts?
Yeah, and before that you said you want to add, all these, the improved demand plan. Because what I'm seeing is there's a kind of a crunching. This is what AI does best, right? The efficiency optimization is working great. And I had a question about the effectiveness, where the humans are concerned, right? Because when you have the sorghum, when you have all that, then you want to make sure it's being distributed.
Yeah.
So the two separate questions. One is how do you tighten the efficiency? How fast it's going to take? And the other one is, and really quick, if you can answer it, if there's no time, that's fine. I can talk to you offline. But how do you add that effectiveness portion or the human element to make sure it's reaching the people that it's supposed to reach?
Yeah. So. Okay, so regarding the first step, so we have a kind of timeline of the development and productionization of kind of a final version, say by the end of the summer. And we are already working with the Regional Bureau of Dakar and so West Africa and the Regional Bureau of Nairobi.
Ladies and gentlemen, I would like to bring your attention to a starting session, room F on the 3rd floor, discussing large language models and fine-tuning approaches for digital public services. It is starting now. It's very interesting. Come on.
Great. That's great.
So these things are happening all in parallel, and of course, it's also an iterative process. So we have, for example, a colleague that works especially with the super nutritious food, which is testing Scout while we are also developing and adding new features, and maybe she's just giving us a feedback result. I mean, it's not really coherent with what I expect. Or this feature would be nice to add in the web interface because I cannot add this filter, but I really want to add it. So it's a really an iterative process, but we aim on having a workable version by the end of the summer. So.
And actually, I'll take back the effectiveness and just want to add, what about extending it to other things like Bill Gates, he talked about like millet and other things that are not traditionally, people are really leaning back into some of the things that are very indigenous to make sure the food supply continues, including in Africa and stuff like that. So I wonder if there's a way to, innovate and kind of keep that channel open to.
So yeah, so this is a bit, this is very interesting. So how it works, at least how I believe it works, is that there are different activities for WFP where we provide assistance, and then is the Department of Nutrition that kind of creates a food basket for each activity. So then in the supply chain kind of department and us, we try to, based on those requirements, try to fulfill the needs. So that is kind of course, we work a lot together, but it's more on the nutrition department to decide which commodity. There are, of course, commodities and goods that are interchangeable. So, like between cereals, for example. But yeah, we, at least not our department, decides which commodities. Thanks for the question.
I was just wondering what kind of data you're working with, because I think like for what you're trying to forecast, it's like kind of complicated. Like there's a lot of different factors that can affect like supply chains for food allocation. So I think if you wanted to actually use like data-driven models like machine learning, you would have to have like a really, really large amount of data so it can be generalizable, like both like in time and then also spatial coverage. So I'm just wondering like where your data is coming from and like what the actual like spatiotemporal coverage of it is.
So what we are using so far, so for example, for demand forecast, suppliers, these are all data that we have in our WFP system, because it's all the history, WFP purchases, all the suppliers with which we have long-term agreements. So we have all the information available, like about the, and also the network. So this is, I would say, a kind of complete data set. Of course, if we wanted to add information about, for example, food security, we could use, for example, WFP food security data or FAO data, and climate. Of course, we would need to rely on somebody else information.
So it's like decades of coverage, you'd say?
Yeah, so for example, for what concerns the demand and the purchase, we have 10 years of data or even more. Like means at every month, which commodity was purchased, from when, from whom, in which amount. So that is like millions of like rows of information.
Excellent.
Either one long or two very short.
Okay, yeah. Thanks for your presentation. I was curious about the stochastic approach.
Yeah.
Of course, it's the right direction because you should optimize an expectation. The uncertainty is very high in this context. And are you going to rewrite the evolving gene, like in favor of some Bayesian framework, or just having multiple trajectories, like optimizing the computation time? And
so I'm not the person who is writing the engine. So we have one of my colleagues. I'm happy to connect you with, if you're interested. I think he's rewriting the engine like from after the pilot, which will be able to take into account the uncertainty. So I guess with a Bayesian method. So I think I'm not 100% sure that he has envisioned this to already takes into account. So with, I think a Bayesian approach.
thank you so much.
But I'm happy to connect him with you if you want.
One last.
Yeah, it's really interesting. And I just wonder about the kind of trust, this looks very kind of potentially really powerful, but what issues do you have with kind of getting the country offices, regional bureaus to kind of trust the model and build that with colleagues who may kind of go, well, this all looks a bit magical?
Yes, so I think here the key is indeed to really work together. So we have, for example, for the Regional Bureau of Dakar, so what I show you, well, use case, we really have somebody working there, which is kind of our partner, let's say, where we look together at the results. So we compared with the previous plan, because of course, having all the data, historical data, what we can do is to kind of position us, back in time and say, okay, that is the decision you made. What if we have used Scout? Okay, and then we run this analysis, like we kind of forget about whatever happened afterwards, but we position ourselves back in time. We run it and we say, okay, if you would have used it, we could have saved, and we would have picked this solution, which is the one suggested, we could have saved this amount of money doing these decisions. And this, I think, builds trust, especially when, test it together. I would say when it's not that you, I'd say like you bring a product and it's okay, you need to use it, but it's more like we are developing, let's do it together. I mean, we kind of write the code, but like, let's check the results together and
Okay, thanks for talking. The discussion was really nice.
Thank you.
To see that this data-informed work really concretely helps the situation. So now we move backwards from the humans to the vegetation, later to the climate. So the next speaker is Vito Spencer. We will talk about maybe manage better than the website. If what you're slow. What? Vegetation forecasting for anticipatory action.
Yeah. Yes. Hi, everyone. My name is Vitus, and this is really joint work together with Christian, Claire, Lavrov, Melanie, Marcus, and the Max Planck Institute for Biogeochemistry. But before I dive into geospatial vegetation forecasting for anticipatory action, I want to get a better feeling of like who's in the room. So I'd like to ask you all to briefly stand up. Let's get warmed up here. And then basically, I'm now going to mention like a group of people, and that people should keep standing and everybody else sits down. So who of you has been working with machine learning? And everybody else sort of sits down again.
So,
the ones who work with machine learning stand. Okay, that's cool. Okay, everybody back up. And who of you is sort of working in the humanitarian sector? Everybody else sits down. Okay, that's cool. Everybody back up. Who of you has some experience with geospatial data or with remote sensing, with satellite data, that kind of stuff? Still a lot of people. Interesting. Everybody back up. No, penultimate round. Who of you is working with weather or with climate data or that kind of stuff? Okay. And final round, everybody back up. Who of you has not been mentioned in any of these categories? And everybody else can sit down.
Excuse me, are we part of the sample?
Yeah, so basically, if you've not belonged to any of the groups, I'd really love to hear like where you're coming from. So I know you're a reporter here for us, right?
Yeah, I have no background. I have no idea.
Any other interesting backgrounds? Okay, so we're still a diverse crowd, but really on topic. So after we've all warmed up a bit, I want to start maybe discussing. So this whole day is about AI for early warning. But I personally sometimes feel like, okay, maybe it's a blessing, but maybe it's also simply a curse. So if you look at this meme, and maybe that captures like one of the aspects that you could think about it. And so I actually asked ChatGPT about it, but I asked ChatGPT to generate the meme for me afterwards they made the meme. So I was wondering if there's like any comments or thoughts on this in the room. People sort of, what do you think? Is AI really gonna be the,
Yeah, I think I brought this up earlier when I was talking about cost efficacy, but like, I don't know, like there's entire like data teams where people are getting funded like upper middle class or like middle class salaries to like make marginal improvements on models. And then sometimes I wonder like if your baseline is like number of lives saved per dollar spent, if that's like the most effective use of money. Like in some cases, like maybe it might be better to just do like transfers of that to like aid for like a less effective model. Like I think like on the margin there probably is a line where like you're spending too much on like R&D and like that the marginal improvements just aren't like worth it. But I don't know, that's my experience.
yes?
I know, and I have that same thing with you because what about the accountability and transparency? Because I've 4 years and half the stuff never really gets implemented. If it does, it doesn't kind of reach the person. So I think that portion to extend that in this new world is so important to learn from that past.
Yeah, that is very important indeed. Any other thoughts? Anybody would like to share burning in your heart? Or are you always still, yeah, please go ahead.
Of course, I think AI model, let's say the cognitive capabilities could be, let's say, on par with a human one, but the scale is completely different. So and you should not get to a point, but you should look to a trajectory. So where we will be with AI for humanitarian causes in 5 years or in 10 years. So it's not just what you can do now. It's not just the cognitive, but the optimization, like of capability of bringing you up to decision in uncertainty.
Yeah, okay.
I would also comment. I mean, just my perspective. I'm from Max Planck Institute for Biochemistry, so our research is actually not funded. So it's not taking away research from humanitarian action. So if you basically can add with our research to that, I think then the cost and effectiveness is infinite because the cost is zero. So maybe that's also an answer to that. And I think we probably the community should maybe work also more together. But I agree. I mean, one should balance that.
I'm not sure if I'm gonna be able to really explain my idea, but I think there is a very big problem inherent to the humankind and how our mind works towards the risk. And I mean, it's what makes insurance work. And like all the economical model of the insurance companies is based in the fact that we are not able to see and it connects with the first introductory thought. We are not able to see or to prepare for big unprecedented events that really affect our lives. So it's really hard to convince governments or people to fund things that it's hard to tell that they will happen because they may happen or they may not happen, and they will affect this way or this other way. And like where there is uncertainty, there are barriers in our mind that just makes us let's spend funding in something else.
Okay, that's
one just quick comment. Two things. One is tech solutionism. I see that kind of what you're saying here. That's maybe perhaps not the answer. You don't want to take the human out of the loop when you're actually trying to do the humanitarian action.
That is actually a really good point. I think that's also important why we are all here in the room to discuss sort of on these aspects. Nevertheless, I want to talk a bit about the blessing, or the part where maybe AI has already worked. So one of them we've already briefly seen in Marcus' talk is using large neural networks for weather forecasting and implications for early warning. So for instance, there have been emulators of global models. So they use this ERA 5 data set, and then basically you train on that weather forecasting afterwards. And that has implications for tropical cyclone track forecasting. So this is an ensemble from the GenCast model, and actually their track forecasts are better than previous conventional models, and that's of course very important for, let's say, early warning. On the other hand, there are also these regional models doing radar nowcasting, for instance here the nowcastnet from the Chinese group. And as we've seen in Marcus' talk, extreme precipitation events can really have severe impacts. And this is another aspect where we've already seen that neural networks can do a lot for early warning. On the other hand, on geospatial data, and seen some of you in the room currently work with geospatial data, we've seen this sort of foundation model approaches. So these are AI models, machine learning models, that you train on the task of in-painting, of gap filling. So you artificially mask out a lot of parts of your data, and then you try to reconstruct that. And that is an unlabeled task. So you can really just do it on a large database that already pre-exists, and you don't actually need to collect more labels. But it's very efficient to afterwards fine-tune the model on any task that's sort of mapping. So for instance, you can do flood inundation mapping, or detect where there are flooded areas, but you can also do it literally anything that creates a map and where you have some sort of labels. These sort of approaches work quite well. So if we look at the early warning chain that you've already seen before, where does this fall in? The weather is sort of in the weather forecasting area, of course. And maybe the geospatial approaches are really important in the impact forecast, where you need vulnerability maps and so on, exposure maps. But what about the whole chain? What can you do about that? And we've been thinking a little bit about it, and there's actually a treatment online that if you are more into the research side, we'd love to discuss with you. And maybe just briefly recap. So we have these methodological models that take weather at some time step and just forecast into the future. We have geospatial approaches that take satellite data, and then you can perform mapping. And then what we sort of maybe say for early warning is actually you need to integrate both of these modalities and maybe even add further modalities, something like socioeconomic data, maybe text data also, so natural language, or even go to like images, videos, and so on. And we've seen a lot of success from generative AI on like the bottom part of this half. So maybe if we can integrate the top half, we can actually go to early warning models that can do risk mapping, impact forecasting, and communication. And in this talk, I want to zoom in a little bit. We haven't done the full foundation model yet, but I want to zoom in a little bit on integrating metrology and geospatial data for impact forecasting. So the particular example that I'll talk about is geospatial vegetation forecasting, where you take some past satellite data, some metrology from both the past and the future, so including a weather forecast basically, and some elevation data or any additional auxiliary data that you might have that might be predictive. You feed all of that through a machine learning approach, and I'll go into detail later what exactly that entails. And then you can predict the future vegetation state. So basically, you just predict the satellite data into the future because of that. Again, you have a lot of data available. And these sort of approaches require sample-based training where, okay, this is a map of Europe. And so because we started sort of in Europe, where you collect a lot of samples around, well, in space, and then you train your model at all of those places and then hope that it extrapolates both in space and in time. And of course, you don't just hope, you actually test that. So you create test sets that are sort of far away from your training data to check really the robustness of it. And the type of satellite data that we rely on in this example is coming from the European Space Agency. So this is from the Sentinel-2 satellite mission, which has up to 10-meter resolution, 5-day revisit time. It's in orbit since 2015, so maybe around 8 years of data now. And it has 13 bands, mostly in the visible light, but also some more red edge bands and shortwave infrared. And well, for machine learning, you need to compile that into some analysis-ready data set, and we've actually started doing that already in 2021 with the Earth in 2021 data set. I'm happy to say now that is out of the way, and we've replaced it with the Green EarthNet data set, which is basically an updated version, and we really hope is going to push us towards geospatial vegetation forecasting. The idea here is that it integrates satellite imagery, metrology, land cover data for the first time, and elevation maps, and also Sentinel-2 satellite imagery actually is optical satellites, so there's a lot of clouds on there. And we found that existing cloud masking algorithms are not always perfect. So we trained our own neural network to do the cloud masking for us. And in the Green EarthNet data set, actually, hopefully have what I consider a fairly good cloud mask, let's say. In total, we collected around 25,000 of these mini cubes, so locations around Europe. We do like 150-day time length and 128 by 128 pixels, really for machine learning models, sort of nice and handleable. And overall, it's 200 gigabytes in compressed size. So still manageable, let's say, for academia, but already a little bit too large scale to do on your own laptop. So you do need a. Now that we have the data, let's look briefly into some models that you might want to use on this. And of course, you always want to start with baselines. And maybe the most naive baseline is really persistence, because vegetation, it does change slowly. So you just predict constant. You could predict what was happening in the previous year, so sort of previous season baseline. You could use the climatology, and this is would naturally be the strong baseline. However, for Sentinel-2, so I mean climatology of the vegetation, right? And this comes from the Sentinel-2 satellite data. And we have a little bit of the problem that there is only 8 years of data. So how do you construct such a climatology? We came up with sort of a leave one out fake approach where you look at all the other years and then construct something, over smooth it heavily. And we found that that works, at least. It looks like climatology, let's say. Then other simple baselines are already neural networks, like long short-term memory neural networks. So those are recurrent neural networks that can process temporal information. And also coming from time series forecasting, so more from economics, those of you that maybe work in that area know these models profit from the Facebook and are really good at forecasting cyclical data. I've mentioned before that we had a data set already in 2021, and there have been other groups that sort of developed models on that data set. And we took the top models again and evaluated them on a new data set because well, I didn't like the old one anymore, and I was a little bit worried that it wasn't strict enough. So now with the improved version, I was wondering how well do these models do? Also in comparison to video prediction methods. So in AI research, or in like mainstream AI, let's say, a lot of the people that do spatial temporal models, they actually focus on video, because that is spatial temporal data. But you could argue that satellite image time series is sort of similar. I don't know why it's so shitty resolution, but so sorry for the word. But it's sort of similar like a video, right? It also changes in time. So we wanted to check if those methods transfer or if you really need to develop your own method. And well, surprise, of course, we needed to develop our own method. So this sort of, I'll show the results a bit later, but the whole idea here is that for time series forecasting for vegetation, it's really this time first, space later principle that maybe applies, where really the temporal information is super important, but then spatial information might also play a role, like spatial context. But you can separate the two, so sort of the space information is maybe more static time. And we did that in a transformer model. And transformers, if you train them on 3D data, it's really messy because it's very computationally expensive, but if you split it between time and space, then it's actually possible. So what we did is we first processed in space with sort of a vision encoder, this time and vision transformer for those of you in more of the AI world. And then we used masking. So I briefly explained before that typically transformers, you train them with like this random dropout masking. We do that. We apply a cloud mask. We add the weather information that we feed to another neural network to encode it sort of in a high dimensional latent space. And we also add some temporal positional encoding. First, the hard piece of our model is the temporal transformer that really per patch, so per part of the image, translates it through time. And because these transformer models don't naturally have an idea of positioning, you need to add some positional encoding to make it realize that one of the patches is before the other one. Then we add some more like, let's say, priors. Here, like we say the initial prediction should sort of be the last valid pixel that we've observed from the context period or from the historical period. And then we just predict the delta from that to achieve sort of vegetation predictions at future timestamps. And of course, I wouldn't introduce this model if it wouldn't be the best on our benchmarks. So it is. So this slide is maybe not that interesting in that regard. But here we briefly show like 4 different metrics: R squared, mean squared error, natural efficiency, and the absolute bias. And the red one is our model is better than all the other models. But most importantly, this climatology baseline that I mentioned before, that I think is really the one you should compare with, is here in the dashed line. And our model beats the one. But interestingly, the previous state-of-the-art approaches, sort of in orange, they are not always better than the climatology. So we were first sad to see that, but then happy that we managed to beat it and go to maybe some place where we can actually predict anomalies beyond the climatological mean or the seasonal cycle. And then these models, you can apply them in sort of these worst-case weather scenarios. So here brought a location in Greece, and we're going to look at the early growing season of 2022 and just run through some scenarios where from the top left to the top right, there's no precipitations or no rainfall to a lot of rainfall happening throughout throughout this 3-month period. And then from the top row to the bottom row, there's very cold weather to very warm weather. And we sort of see that the vegetation develops very differently but we also see some local patterns, like on the north-facing slope, closer to the river, there's maybe more resilience of the vegetation to extreme weather conditions, whereas on other, like south-facing slope or so on, it might be that the vegetation dies off really quickly. And we hope that this sort of scenario approaches can maybe bring us towards anticipatory action or help there. So briefly, what is anticipatory action? The idea is if you have any sort of indication that a disaster is happening in the future, then the natural thing to do is you act before the disaster happens, right? Because, I mean, for two reasons. First off, you can really save a lot of lives and you can protect a lot of livelihoods if you do that. But second, it's also just way cheaper if you act in advance. So maybe one example how our work could feed into that concept is that you take sort of the weather forecasting ensemble, but you don't stop there, but you feed it through our vegetation impact scenarios. And then you have sort of a vegetation indicator at community scale. And for instance, the VCI 3M, I will briefly introduce in the next slide what that is. If that is below a certain threshold, then agencies could trigger and maybe do something, distribute drought-resistant seeds, but I really know nothing about that probably. WFP would know more. Yeah, so what is these VCI 3M? So the 3-month vegetation condition index. This is actually what is currently already used by the Kenya Red Cross for anticipatory action. And so there are two aspects here. First off, I mean, we want to try our models in sort of this real-world scenario. And second, I realized that they use the MODIS satellite at 250-meter resolution, which is going to end its mission soon. Now, actually, it's already sort of out of orbit. They're still sending some data, but it's getting worse and worse. And in like 2-3 years, there will not be more data for MODIS. What could be used instead? Maybe the Sentinel-2 that I mentioned earlier. So if you have the Sentinel-2 data, how do you actually compute such 3-month vegetation condition index? And this is really technical now, but I want to give you a brief insight into geospatial processes. So this is the raw Sentinel-2 data. And you see a lot of clouds, and you might wonder, okay, I'm not even sure that this is very useful. So the first thing you really need to do is you need to cloud mask it, and then we compute the NDVI, which is sort of a vegetation index, so indicator how much vegetation there is, but how green the vegetation is actually. So then you already see you end up with a lot of data gaps, but at least you maybe reduce the noise level. And then to get to the vegetation condition index, which is a relative index, so it sort of shows you historically how is the vegetation doing at a certain place compared to the minimum and maximum climatology. So you need to compute this minimum and maximum climatology. And we only have a couple of years of data, so 8 years of data. So we came up with a method where we really oversmoothed the data and sort of computed these values, hopefully somewhat sensible, to then actually get this vegetation change or vegetation condition index, VCI, and you smooth that over 3 monthly windows to achieve the VCI 3M in the dark green line here. And then in red, you sort of see the areas where it's below 35%. So this is the threshold set by the Kenya Red Cross for anticipatory action. This is where you have drought. Now we want to forecast this index. And this is actually, I didn't mention, but this is a location in Somalia. So we're now looking into Somalia here. And so I've tried our previous baselines. Sort of, this is the model that currently is used by the Kenya Red Cross. It's from Kazat et al. From 2021. And they already tried it on MODIS. So let me try it on Sentinel-2. It's a linear model that literally just forecasts, given the past value of the vegetation condition index, how the future is going to look like. And you can see that at maybe 8 weeks lead time, they still have a fairly good skill of 0.76 R squared. But then, of course, the more you go into the lead time, the worse it gets. There's also a follow-up work from the same group in Great Britain, which they call the ARDL6 model. So it's taking into account the weather also in addition to the past vegetation condition, but only the past weather. Actually, they used past soil moisture and past precipitation. I would argue that doesn't work operationally because the soil moisture data they use is not in near real time. It's only available a couple of months after, with a couple of months of delay. So that's probably also why this model is not currently being used operationally. So what I did instead, I actually used weather variables from metrology that you would actually get in near real time. So I adapted the approach a little bit. And you can see that it improves the R squared slightly, but not super much. So like 0.04 R squared more in this kind of models. And okay, this is just a local example in Somalia. If we want to try our deep neural networks that I've mentioned before, like the context former, we actually need to train continent-wide because you need a lot of samples. So in our European project, the Deep Blue project that's just finished, we actually constructed a data set on all of Africa, and we are preparing this for release now. And yeah, so hopefully next time I can show you the results of the deep neural networks. As a summary and outlook, we've seen that geospatial vegetation forecasting is about linking weather to impact on vegetation. Deep neural networks can outperform baselines, so that includes some skill on anomalies, which is pretty cool for me at least. So this might help you towards field scale drought impact forecasts, for example, on pasture, because there you could do pastoralist drought anticipatory action, which is something that I think currently is not really implemented yet. But if you use the vegetation condition index, then maybe you can move forward there. Thank you very much. If you want to reach out.
Thank you for the nice interactive part and some machine learning on what you're doing. Any questions here?
Yeah, so I'm not sure if I quite understood like whether you're using like weather forecasts or like past weather data.
I removed the slide just right before so I thought that I'm over time. We develop these models only on past data because we say we're interested in this link from weather to vegetation. But if you apply them, this was sort of also this colorful plot with these different weather scenarios, then you would actually use weather forecasts. What I've not tested yet is how good are these models with weather forecasts. And this is definitely on my list to do. It's a lot of data to get all the weather forecasts. That's why I've been slow there.
Because my main question would be like, if you're using weather forecasts, then like, how do you kind of deal with compounding uncertainty? Because those forecasts themselves have uncertainty associated with them, as does yours. And if I think you're also being slightly like autoregressive, or you're using like future predictions of like vegetation to inform like future predictions, like if you're going like further, you want like a full longer lead time, like you just end up basically like with like exploding uncertainty where the model is just like, oh, it'll be anything from like 0 to 100, right? So
Maybe,
how do you kind of deal with that? I guess like I saw the scenarios, but normally what agencies want if they want to do action is kind of like a point estimate with like an interval. So I guess how would you deal with that?
Yeah, I mean, this needs to be addressed for sure. I mean, on the why we still think that maybe it's valid is that the land surface just changes slower than the weather. So it can actually be that at seasonal timescale, you get more predictability on the land compared to just atmosphere.
You have mentioned that you are using Sentinel data. Are you planning to use any other kinds of data, like, for example, from UMETSAT meteorological products to complement your forecast, like Meteosat or Meto?
Yeah, they have these very cool geostationary satellites that actually measure the Earth, I think, every 10 minutes or something. It's insane amounts of data. That would be really cool if you could actually use that.
You can.
I know. It's more of a technical challenge, right? So I don't know. You have experience with?
I work for UMETSAT. Yeah.
So let's talk together.
Yeah.
That would be cool, yeah.
All right. Thank you for the better presentation. I have just 2 questions regarding on 3-month vegetation condition index. I just saw you have been set less than 35 as threshold. Is there any key metrics you look for while you said that? This is the first question. The second question, I just want also to know what about the robustness check of your data index? Is there any key tools you use for checking the robustness check of the result? Can you put that?
Okay, so for using that index, that actually came from discussing with partners from the humanitarian sector, so from the Red Cross. And after talking to them, I realized they had published a bunch of papers in like 2018, 19, 20 on why exactly they use that index, why exactly, and compare it to other indices and check how well it sort of actually correlates with pasture condition on ground. So they went on ground and measured that, compared it, and then also what is sort of the threshold that you need to set. I think there is for sure is some sort of compromise between having a simple threshold for policy reasons and something that is actually scientifically meaningful. And I personally haven't done research on that.
Okay. So about the robustness check?
Of our models, yeah. So this results on the VCI. I mean, for the local models, I would say these are really, the two models that I showed are really pixel-wise. So they're very local. So you can, I checked at a bunch of different locations, but it's not that important to check the spatial extrapolation because you can't really overfit them compared to deep neural networks. For deep neural networks, we need to do it, and that's why I haven't shown the Africa results yet, because we want to be extra sure that our models is doing well.
Yeah. All right. Thank you.
I just have one comment, a sentence comment. That's all. I just want to say, like, in the humanitarian field, it's widely known that almost 2 billion people are almost in famine or going into famine. So when you have the 3-month warning, right, we are way past that warning on some significant. So I just would leave that question on the table, like, how is whatever we are doing in research impacting the people that are already in a condition? So we can sit here and do research all our lives, but as long as we are not impacting them, how can we do that as well?
Thanks. I think this is a nice closing also to the sort of introductory slide that I had, a bit controversial, right? Because I think we need to be careful here, right? We put AI everywhere, but it might be that for the people on the ground, it's really just food that they need.
This is good, simultaneous. Both.
Yes. So I think we break now for a coffee break. I'd like to reconvene 11. We have 2 more very interesting talks that come from the climate perspective, which is of course super important. In doubt, ignore the announcements that you should go to the stage. And yeah, looking forward to the next part of the session, which will then go until the end as well.
Only twice.
Please. So I stand up and sat down at the same time. Yeah, it's yeah, it's a hard thing.
Yeah, of course. I need to scan your.
Yeah, I just got called into like an emergency like meeting at the University of Reading to build a forecast for South Sudan. Like a situation.
Oh yeah, that's
I don't have the. I still work. This is your channel.
you know, the infrastructure themselves are super everyone has good work forecast. So things are extremely elevated and it's actually just really complex. The idea is that you're able to they're also a bit
You mean on the presenter?
On your on the weather cloud or no?
And try looking at geostationary satellites, and first of all, there's a lot of different levels of products, so I wasn't sure which one to use. And then second, I'm very much into this cloud natives, where you can access small parts of an image. And I wasn't sure how well that was working. Okay.
Like totally unrelated to climate. It's like mapping public transit.
Yeah. Just going there. Ah, okay.
Wow. I wasn't aware.
70s.
Cool, yeah.
Something that's
I think it's a big
for you,
question though,
mining
because
for you.
honestly, from like
Right.
previous experience, a lot of like
fire.
Yeah, true, yeah.
That's
interesting.
Yeah. So we have used another one totally different product, but it's really nice. If you're interested in the vegetation condition, at some point during the day, there will be no cloud. So it increases a lot
The coverage, yeah.
The coverage,
Especially in the
that-
tropics, I think.
that's really nice, but it was only one project. Yeah.
I don't know what like
Yeah.
Yeah.
But maybe somebody wants to know.
Oh, what's your name?
We come to later. I'm in the booth.
Ah, you have a climate science group here.
No, I am Ellis. I'm in the atmosphere. So I'm the partner of farmers.
Ah.
Here as a private person.
Ah, yeah, but really cool. Yeah, we talk later. Yes.
Okay,
Okay, thank you.
Quick question I have. Sorry. So basically, we were interested in the light next over.
Okay.
Industry respect.
I see. Yeah.
I have kind of come from about interest in
They're also have applied
Not yet.
solutions when it comes to honestly speak stuff.
I guess where I'm there.
I recommend reaching out. They also have like all their like stuff.
And
More for me. Fact, there are a lot of out there. Some
I'm a researcher. I don't. Yeah, I would have to collaborate with somebody. I mean, it's gonna come. So it seems to be a very like this parametric insurance, like index-based insurance. It's a very similar concept to anticipatory action. Yeah. So in principle, you could probably use similar approaches. That said, we're not very good on crops. Well, thing is,
a crop specific
to predict crop or crop yield, you need to take into account what the humans are, right? Is that the management is sort of like in Europe, surprisingly, the models are very good because from the rain data, they can predict when the farmers are going to do their decisions because farmers are somewhat predictable. I still find it, I mean, to use the predictive model there, I don't know.
We know
challenging.
if you're interested in the area of
do you actually actually tell you what you think?
maybe it's good that
Or do you think
for insurance?
I mean, I don't have but we can maybe notes my select soon. Then we can like
yeah, so there is a
So you should fly aquarium.
Yeah.
What's
Yeah, and that's the debate between like we've seen a lot of people use deterministic versus stochastic modeling, and it's like we ask them, do you actually understand the type of model that you're using?
You cannot have an answer. When you have decision driven and you
see her.
Yeah.
Yeah.
I mean, you're an officer.
Yeah, I guess that's part of the conversation. We're trying to create that solution.
My first semester. On topic, right? There's different opinions. I think there's some people who are skeptical, and then there's others. I mean,
I do enjoy it, especially because the subject is very fascinating. It's about the emergence of this.
Like everywhere, you need to find the right problem. Because it's a hammer.
Come from somewhere.
It's really data science. It's really I'm trying to conceive models and intelligent simulations. So I'm using as a simulation to see how they behave. What are the factors leading to drivers?
Do you grab one?
It's close to it. Just the thing is, so it's agents exactly the same.
No, no,
it's not a perception that they take actions to but they learn something. Because I want it to be really fully explainable, which is not really the case with smart learning.
It's really not just talk, but I could imagine that you want to use drones because the satellite data is low resolution. Like it's fancy.
It's not really an optimization.
Yes. So maybe you can see something like if it's a
to say, okay, but first let's see
don't need the satellite at all. Farmer house.
and see if
Right? And your whole field is sort of
well
past.
So how long will you take that? Like why?
The capture has 1 year, but
the risk you should be
to the end.
probably depend on that, right?
So the figure
Something like
not sure. I sent a paper yesterday, but
I think they are really working on big stuff. I don't
know. Like you're able to
that's usually
it's
sorry?
and that's also, I mean, Latam is
Also a student
Federation of Iranian
psychology.
and they're sort of all independent, but
Very cool.
so maybe there's one of medicine where they
Where?
in Paris.
In Paris?
The
whole maybe you said that. No, I didn't. I was like
That's like invitation. Thanks for your nice contribution.
oh yeah. Maybe I misunderstood.
how to optimize inversion systems with treatments and the result. Sometimes it was how to feed insects and that's by mixing the waste. They will lead to a good ratio of protein versus at the end of the back.
Oh, so smart. But it's just like in terms of natural, like in liquid waste is what you're saying. Like in a landfill.
I mix a lot of things. Sorry. Like insects, what they did is that they buy they feed insects with insects, but they have to choose the amount of which waste to give to the insects, because and they can choose beforehand for this sort of they wanted to need to
like processes so it's really just taking the and then two and having thinking some other product. I'd be skeptical about what these new effects right? Because maybe they're just something information or something because you can't there's not more information right?
At the end.
However, if you use additional like central one information or other satellite to drive that, you can do a lot more.
It is it's the anxious subject.
It makes sense. So mine is so I'm doing my
I think they used the area
I'm using like the first data because a lot of people use it.
huge amount of data.
Exactly. They learn the statistics. They don't learn the particular realization, right? So even better would be you take the time series of Sentinel-2, you take from the same location the area that maybe could happen once, you collocate that, and then you actually have
There's one's just for
it's still very difficult to do that. How do you need a foundation to do that? instead of interpolating and just hallucinating, we actually know how it looked at one point. Just actually
Actually, MRI notation and to map the reports to the MRI emissions, but automatically. So if there is some everything in the report, it says that there's
one sheet which was not
straightforward. But yeah, I love this. It will be like
less problem.
the center, there is a lesion, like 5 centimeters. We try to extract that from the report and map it back to the.
Yeah, I don't know. It's a multimodal.
Yeah, it's like very difficult
Maybe I should check more.
that
the image and the text.
Yeah, thank you. Well, what's your?
like I'll like yeah, sometimes what is this? And then so I that's like when we start.
I don't know, like this sort of
But it is very possible.
real.
Okay, originally
Yes.
now she's
Oh, yes. A bigger problem is 3 months, but see what Google be able to reach. But I don't think. Yeah.
Oh, yeah, yeah.
That's good. That's good. Yeah. Well, enjoy the rest of the workshop.
Which is now we're doing at the moment. For us. Yeah, that's the That's right. Yeah. Yeah, I chop it off. Yeah. Oh, I know.
Well,
it's like research in between.
So we're gonna now
Last year is specialization. It's better to know whatever.
Very good.
I will
Very good. Thank you.
mixing computer science and psychology to better understand and especially emotions. So what I will do next year is that I will take cognitive and decision sciences last year. I wanted to ask.
You have to take the stage data and the ground and you interpret it. They use an ensemble method. I think I once ran like not the ensemble, but the uncertainty of the need.
It's always do that.
How do you think? It's always hard. If you do half-hearted experiments, you never know what to do.
Yeah. I have the glad you didn't take. Yeah, I think it's do you want to give it as much information as possible?
Yeah,
that's really good for compromise with those but to not change what the error is, try and I don't know, it's a
I want to actually this is taken, this C3. Go ahead. And on the other side, I think this, I mean,
yeah, they sent this application so that the students can connect with each other.
Okay, let us continue with two extremely exciting talks. One from Kai, and he will talk about actually the increasing complexity of extreme debate on the climate.
Yeah, thanks, Marcus. Thanks also for sticking around. It's really exciting event overall. Thanks also for all the organizers that made that happen. I'll talk a bit about heat waves, how they changed in character under warming conditions that we're living in, and we'll talk a bit about our confidence with reproducing them in state-of-the-art climate models. And this work done in collaboration with Yingyan Tian, postdoc at the Institute, and Julian Eisen, a master student, who are both working in the Climate Stream project that I'm leading. I'll start with a little overview of the past years. Climate with regard to extreme temperatures. So as you probably know, 2023 was the hottest year on record so far, which also featured a lot of surface extremes. 23% of land areas were affected by extreme heat, setting new records. So models have been pretty well in reproducing the average climates regard to global mean temperatures. And 2023 was one of those years where it actually really kind of tickled the margins of the uncertainty bounds there. Still within them, if you correct models for the transient climate response, but it certainly was one of these edge cases. So again, this talk, I will talk a bit about the regional extremes and how our confidence is within the climate model. So maybe a bit of a theoretical overview. We know that extreme heat in particular is changing due to different reasons and how global mean warming is affecting regional statistics or distributions of temperatures. So this can happen through just a mere shift in the mean, which then leads to more extreme tails, of course, but also changes in the variance and the skewness of the distribution will affect the tails and lead then in combination to more extreme heat. This is then compounded with other effects, which I refer to in the title of this talk when I talked about the increasing complexity, because heat extremes are also preconditioned and amplified by other effects that we do see happening globally. And this is the seasonal and spatial expansion, the concurrence globally, and also their subsequence, which just leads due to feedback mechanisms to higher levels of extreme heat waves. I want to talk about these types of record-breaking waves because they are often those that are associated with the most extreme impacts, as we already heard. So I really like this plot because it gives you a very good overview of the types of extremes we have been experiencing. So this the land area affected by extreme weather, ordered by the extremeness, let's say, by their sigma. So like how far away from the mean the levels basically are. And as expected in a warming climate, we do see more land area also affected by extreme heat. And what I find remarkable is that certain types of extremes really just have started to emerge very recently. So these 1 sigma extremes we could refer to as normal extremes, so to speak, stuff that is expected as part of weather and variability. And just in the 80s, these types of 2 sigma events really started to increase, and other extremes like 3 sigma events, they were really not available or present at all before the 80s, right? So these are really these types of unprecedented extremes I'm talking about. And just now, starting with the new millennia in a way, we do see these 4 sigma events. And one of these types of events, this was actually a 5 sigma event, occurred in 2021, the Pacific Northwest heat wave, which really shocked climate scientists as well, I have to say, and also led to like cascading impacts through wildfires and air pollution. leading to a spike in emergency room visits, and also devastating effects on the biosphere. There were reports on shellfish being basically cooked alive because of the heat. They couldn't cope with it, right? So this event is remarkable because it's so unprecedented, and it kind of crashes our statistical tools to deal with them, right? So usually you can calculate return periods with a generalized extreme value theory. In this case, including this event is just shifting the return time to such a degree that it's really questionable if that's a reasonable approach at all. So here we have plotted return times and how different years kind of place within that distribution, and the dotted line shows the distribution for these return times without the event, and the continuous line here with the event. And yeah, it's a truly unprecedented event that was virtually impossible without climate change. These events are, of course, important to understand, and also it's important to understand where they occur, with what frequency and probability currently and in future climates. And this paper shows that Europe in particular can be considered a heat wave hotspot, so an area where heat waves, extreme heat, is occurring at a higher rate, a faster speed than most of other areas in the mid-latitudes. And we want to understand why that is the case, and part of the explanation can be found in the atmosphere dynamics. So to approach this problem, we used self-organizing maps to categorize zonal circulation patterns, and found three distinct patterns that basically cover the most important states of the zonal wind. Maybe for those that are not that don't have a physics or climate background, the zonal wind is the west to east wind that really carries the weather patterns across the mid-latitudes, and is partly responsible for the fact that now we have rain and tomorrow we might have sun, right? So in the mid-latitudes we have this weather variability of days to weeks, while in other areas like tropics, weather is a bit more stationary. And so with this, we found that a particular circulation type is really increasing in frequency and persistence. So this is this so-called double jet. So two distinct branches of the jet that is encircling the European continent. And this looking like that, more or less. So this is a composite of all these events we identified. And it really leads to a situation where in the center around Europe, there is basically no wind, while the zonal winds are being diverted in the subtropical regions and the more polar regions. And that leads to more stationary weather, which then kicks off feedbacks, and is part of the explanation, in addition to a lot of other reasons which have been since then reported in a bunch of other papers, such as aerosol trends and circulation patterns that are characterized by more local features. Part of the explanation why Europe really sees these amplified heat wave trends, and that's a report that came out after we published this paper that reconfirmed that finding. Now, you might have seen in this initial map, Europe is not the only place where heat waves do increase at a faster rate than the global mean climate. And this gives you a global idea of areas where the hottest 2% of the days annually increase at a faster rate of the upper quartile. So kind of, let's say, moderate extremes. And it gives you an idea of the tail behavior of the distribution. So how fast is the tail warming compared to the rest of the warm days? And Europe, again, as expected, is really sticking out as this really intense blob. So this is again, a confirmation of our initial finding, but there are other areas globally that also show this behavior, and some of them either are the locations of important biomes, or are like really populated areas. So in this paper here, which is currently in review at PNAS, we try to find out to what degree climate models do reproduce these types of trends, right? Because in order to prepare ourselves, we first have to know what type of extremes we actually have to prepare for, and where these hotspots are to be expected in future climates. And this assessment here gives you an idea of where climate models place themselves. So this is basically comparing observations with a large number of climate models with different architectures, so coupled and SST-forced models of different spatial resolutions. And most of these hotspots are really not that well captured, which you can see by this kind of scale, right? So basically, the scale here gives you an idea of where the models, where the observations are being placed within this large range of potential trends in this particular metric. And everything that's dark red means that the observations are really outside of the entire branch or potential trends that models are able to produce. And that can also be shown in this way. Maybe that's a bit more intuitive. So this provides the regional averages over some of these hotspots, and shows like the range of what is modeled versus what's observed. And in particular in Europe, the observations are far outside of the modeled distribution, but also in other areas, and in particular also in high latitudes like Canada and Greenland. That's also the case. Another interesting fact is, this is basically giving you a more global perspective of this, is that really globally trends above 0.5 degree per decade are underestimated by a factor of 4. This is not shown here, but high latitudes and mid latitudes see the strongest divergence. Models are not only underestimating regional trends, but also their significance at a higher rate than observations. So something is odd, something is off there. And to understand what's going on, I think we really need to go back to physics of heat extremes. And this is a figure of a beautiful review from David Barrio Pedro, who really managed to provide a very comprehensive overview of how heat extremes can emerge on different scales and relate to different parts of the Earth system. And I would basically sum that up into 3 potential factors. One is really diverging trends in the models themselves. So this is something that can state for Europe, trends in circulation and aerosols are really strong contributing factors there, but also globally, Simpson et al. Simpson found that humidity trends are really kind of often models, and that's of course also a very strong contributor to heat wave trends. A second factor, which I want to look further into now, are these processes and the type of surface response that we see to extreme heat, and these nonlinear feedbacks that are likely relevant for these very extreme events, those kind of Pacific Northwestern heat wave events that all of a sudden exceed standard deviations of 4 or 5, right? So some type of internal feedback process that apparently just kicks off, and this is running freely. So just looking back on that particular event and what happened there, again from that paper by Sam Bartusek, we didn't see only extreme values in temperature anomalies, but also in soil moisture levels, which were anomalously low, and geopotential height anomalies, geopotential like a measure of local weather, especially. So high geopotential heights are high pressure systems and usually form good weather. And in this time series, you can see that the temperature, which is shown here in orange, was really strong, this 5 sigma anomaly here, but also geopotential heights and soil moistures were really high too. And this framework also leaning on a really nice publication by Erich Fischer, we call extreme anomalies of common drivers, essentially drivers of heat waves that we know, low soil moisture and geopotential heights that are both at the same time showing these anomalous values and then interact with the temperature to lead to these very high values. And in this paper, we also suggest another framework called nonlinear interaction of common drivers. So the fact that during these very extreme events, of which we don't have that many samples, unfortunately, really show a diverging behavior during the strongest magnitude. So this scatter plot shows like the more or less linear relationship between geopotential heights, temperatures, and soil moistures. And during this event, the diamonds here are the days of the Pacific Northwest heat wave. That seems to be kind of taking off into a different regime. And that's, of course, just one event. So it's really a hypothesis at this point, but it seemed to be part of the explanation. And this is also kind of the basis of our analysis, which I want to show now, the preliminary analysis as part of this project, where we assume heat wave magnitude to be function of atmosphere dynamics, soil moisture, and an interaction term between those two. This is a similar plot, very much inspired from Sam's plot, but showing the European heat wave, and it also seems to suggest that something is really diverging from this linear relationship. It's like the end of what's expected when you just look at the distributions themselves. And to tackle this issue, we are using a framework that has been very popular recently, basically explainable AI method that we found in a paper dealing with kidney disease, which is very well suited for estimating, interacting, and compounding factors and providing a direct contribution on an event basis, which linear regression methods also would not be possible. So this is more or less the framework. There has been also a very nice paper by Jiang et al. In Science Advances where they use this to explain compounding drivers for flooding events. Very nice paper too. So we use this approach to then treat Shapley values, which can be then considered as different contributions to the magnitude of the heat event, a direct contribution of the atmosphere dynamical part, then the soil moisture aspect, and then the interactive contribution as well. So again, these are all preliminary results, but the model seems to be behaving all right. This is the European heat wave 23. Again, one of the most intense extremes Europe has witnessed. 60,000 casualties, so really high impact event. And the black line shows the event itself, the temperature anomaly, and the dashed line shows the predicted value and the different interactions that lead to that overall. This shows how the contributions behave when you standardize them or normalize them, and part as a support for our hypothesis. During this particular event, the interaction contribution was really extremely high, so 3 standard deviations And this is also, again, preliminary results, so don't look at the R square values too closely, but this is basically all the events that we find, all the different heat occurrences. And it seems as if in the far tail there's some type of change in regime, that the dependent structure really is affected in a way by this type of contribution. And if you look at different parts of the tail, that relationship seems to be increasingly high. So this is for us kind of encouragement to look further and make this whole scheme a bit more reliable. That's all work in progress. So I'll sum up here. We have an increasing amount of these types of unprecedented extremes, which are linked, of course, by a shift in the mean, just part of anthropogenic climate change. But regionally, these types of interactions between soil moisture, also vegetation, of course, and circulation patterns are really important drivers. And of course, we don't live in a global mean world. We live in locations, cities, villages, and so on. So ultimately, what counts is really to understand these types of localized extreme values. And this seems to be also driven by new types of heat wave regimes, like nonlinear interactions that models currently cannot capture as well as we would like them. And that, I believe, has really huge implications also for these types of risk estimates and reports that we are always leaning on when making policy decisions, right? And maybe also taking a step back, this is essentially the type of impact driver that we think we understand best, right? Because it's so directly connected to global warming. We haven't even started to talk about extreme rainfall, floods, or potentially compounding extremes that make this whole thing even more complicated, right? So maybe a sign of hope, explainable AI can help to shed light on this. Seems to be, signs of nonlinear relationships, and that can hopefully be used to improve early warning systems and also validate GCMs, their behavior, other new things. So I want to close here with a bit of PR. Just started a new theme at YASA on extreme weather and climate dynamics, and some more research on this coming up. Also, RiskCan, get in touch. It's a global initiative that aims at covering the whole risk space with the focus on environmental and climate risks. And so my ways of channels in contact with these groups. Thanks again for your attention.
Yeah, excellent perspective. By the way, on the RiskCon, so I've been sharing that the last 6 years, and it's going over to Kai. So Kai is in the punch point. All of that together with Marlene de Ruyter from Amsterdam and another colleague from Waterloo. Any questions or comments? Sorry that the room is packed again. We didn't get a bigger room. That's how it is. Yes. On two.
Yeah. Oh, I was wondering how you do with like data leakage when you're evaluating the model. So like if you train potentially in the same year that you include data from the year in your test set in your training data, the model might be like learning relationships that are relevant to that year. Like maybe it's like a particularly dry year or something, and it's learning that instead of like actual relationships that you'd be able to like use while like forecasting or nowcasting. So I'm wondering if you account for that when you're splitting the training and test sets, or is it just like all the time goes into the training set?
I mean, at this point, everything goes into one batch. We're not forecasting anything yet, right? It's just trying to understand these relationships. So we're just happy that we have as much data as possible. But we do still kind of think about how to best define our events and basically data points, like what type of averaging can be done, how many data points globally can be included. Should we just look at one type of climate zone because interactions are expected to be very different there compared to like say, alpine regions or whatever. So that's something we think about, but essentially we're not splitting anything. But once we do prediction, of course, that becomes
I was just wondering if the kind of explainability side gave you results that you were expecting. Like, did you expect those results on the interaction term and like the relative importance of the individual factors?
Yeah, that was our hypothesis. So that the interaction term shows this behavior, at least for those very extreme events, something that we thought we might see. Of course, as I said, like the exponential fit is not really giving any better skill than any other fit. Like right now, it's more like a visual thing, right?
So there was nothing like unexpected or in what?
Unexpected was that the models are not giving us what we would like to see. I think that was the unexpected part, which then triggered this research and was more of a confirmation to see this interaction.
Thank you.
Yeah, maybe as a follow-up there, that the climate models are not capturing those extremes, but if it's a high sigma event, would you need an extremely large sample the climate model, and could that just be the reason why we don't see it?
For sure. I mean, in this case, climate models don't capture the trends, right? So it's more
it's the trend.
Yeah, the trends are off, but of course it also affects, or trends are also driven by these very extreme events. Of course, it's not clearly independent, but I mean, we do have one value per year, basically, for each of the models, and so with that, we're hoping to cover more or less sample size. But another big issue, of course, natural variability, and you know, some, especially those that come from the modeling space, saying, well, what we're experiencing here is just one potential outcome of a number of realities, and models cover everything because they might not be in line with all the modes of variability. So I think that might be a bigger kind of discussion point than those that be raised in the reviews.
I have a question. The curves that you showed with the mean and the variance, like, are they local for each place that you analyze, or are they global? And the question is because, like, do you do any kind of normalization or taking into account the actual temperatures of the place? And what I mean is having a heat wave in a place where the mean is, or like 30 is, or 35 is already an amazing number. I mean, you're not going to have the same quantity of death, for example, than if you have a heat wave in South Spain when it gets like 46 or 48, where actually, like, there are studies that show how many people die because of that directly. And like, yeah, like those kind of things.
Yeah, which I'm not sure if I understood what figure you mean. You mean these scatter plots, or earlier pictures, like the more conceptual ones?
Yeah, no, like when you define what an extreme value is, like, is it defined locally or not?
In this analysis, we normalize the data, so it's relative to local climatology. But I'm actually thinking that for physical processes, we need to look at absolute data, because threshold behavior is not, driven by what climate usually is. But this discussion about relative anomalies and absolute anomalies is super important for adaptation. Yeah, I agree. And that's why there's like a huge set of different heat wave metrics, and some are absolute when it comes to heat stress, and there are like limits to what the bud can cope with, usually sweat low temperature values, and then there are others that are more relative, that look at percentile values, and they are probably a bit more relevant for local adaptations. But it's usually both, I guess, that's needed, because infrastructure like roads or energy systems, they usually cannot go beyond certain thresholds, right? So there you also need to consider absolute values.
Exactly, because I was amazed that, like southeast Spain and all the Sahara, like there, like no heat waves on the graphs, and you may think as well because they are already on the limit, like we cannot go hotter. So
yeah, that might just relate to the this is human, right? This just relates to how heat waves emerge there, so that the variance is not increasing as much, or like the tails are not increasing more than the mean, but that doesn't mean that the mean is not also extremely increasing. It's just in this type of metric, we particularly want to look at the tails of the distribution because we think that those are most affected by interactions and nonlinear things, while the rest might just move more regularly with the global mean. So,
maybe one suggestion or comment whether you showed nicely that exactly this can happen through the coupling with soil moisture and the land surface and so on. So one thing that we actually see that there's another interaction, so that vegetation, how vegetation responds in terms of how much it evaporates into the atmosphere. Depends on the soil moisture, but interacts with vegetation. Forests react quite differently from grassland and agriculture. So that might be another factor that maybe reduces some of the scatter in your shaft values there. So we could actually look into this. Yeah.
I guess humidity is a better metric, because somehow relates to both.
Air humidity?
Yeah.
That's a good question, but then it's also not only a cause, but also an effect. So, okay, we talked about it. Good. So we continue. Yes, thank you. Continue with a final presentation by Shrutina, also touching on the atmosphere and climate modeling. AI enhanced approaches in the cloud. So,
a bit laggy. Okay. Hope I've got the right key. So yeah, last talk, and thank you everyone for coming for this session. So it was already quite a few interesting points and discussions that we've had. Hope that we can end it well. So I'll be talking about cloud optimized AI-based rainfall forecasting for early warning systems over the Greater Horn of Africa. And this is part of a multi-year, multi-partner initiative called Strengthening Early Warning Systems for Anticipatory Action. Yeah, and just to sort of give a shout out to my implementation partners. So we work with several people on the ground, and this is a project that's highly focused on the operationalization of this stuff. So we don't just want to use AI and, have a hammer without a nail. We kind of also want to see how we can operationalize it in a very inclusive way. So some of the project partners include the Kenya Meteorological Department. We work really closely with them, Ethiopian Meteorological Institute, and then also the Intergovernmental Authority on Development's Climate Prediction and Assessment Center. So they've been a massive help in that. We collaborate quite strongly with them, and they have a very good presence over the Greater Horn of Africa region. The project itself is coordinated by World Food Programme with funding from Google. And we also work with ECMWF. I myself come from University of Oxford, from the Department of Physics. So that's where a lot of the research and development work is going on. The objective of the project is to explore the potential of cloud-optimized AI-based forecasts and approaches for operational rainfall forecasts over the Greater Horn of Africa. So we're quite cautious in the way we frame it. We're saying we're exploring the potential, and we really want to have concrete evidence building of what the potential exactly is. There's three things that are part of this that I've been working on, which I will sort of introduce and talk about mainly during this project. The first is, how do we actually do this? So the operationalization of it. And as I've mentioned, it's a cloud optimized approach. So I'll talk about how we actually set up the cloud optimized systems, what kind of infrastructure we have, what kind of protocols we're following. The second part is comparing and contrasting the AI models for rainfall forecasting. So it's been quite an exciting and also hectic period over the last couple of months even. So every week I feel like there's a new weather model that comes out, and we really want to have, again, more evidence generation on exactly what the added value of these models are, how they compare, where some of their strengths are, where some of their weaknesses are, and then deliver the best possible forecast over the Greater Horn of Africa so they can actually use it.
Ladies and gentlemen, hope you had a good coffee break. Head on over now to the center stage in room A on the ground floor to see how technology like AI-powered exoskeletons can empower people with disabilities and change the future of mobility. See you soon.
That actually sounds really good. No, I'm kidding. Please stay. And then last but not least, again, we really want to focus on the stakeholder engagement, on actually how we communicate this, on what the actual added value is. So I will talk about how we communicated the rainfall forecast, particularly very recent ones. So there were really heavy rains that happened in April 2024 in Kenya, and also South Sudan, and in Somalia and Ethiopia. So we'll talk a bit about that. So before I go into those three things, I'll just introduce the current model setup. As I said, we collaborate with WF to already provide a range of output forecasts. And what we do is we take the forecast output that they have. So for example, they've got Cape all the way down to the big wind forecast adaptation. And we add a CGAN. So this is a conditional Wasserstein generalized adversarial network. It's an artificial intelligence-based machine that we then use to post-process the forecast. And we calibrate it based on iMerge satellite. So I'll come to this a bit later on, but this is really calibrating on observed data instead of reanalysis data. And we really try and emphasize and focus on that, because that's also what the people on the ground are more interested in, because that's obviously more close to reality for them. Here is an example output. So on the far left, you can, or is it left? Yeah, I guess for you guys, you can see the actual on the ground observations. And this was like a very rainy period, I think, in 2018, November. And yeah, you can see that it was raining a lot. And so on the middle column, you can see the IFS, so the ECMWF output. And at the bottom, you can see the ensemble mean. At the top, you can see the different members that then represent the uncertainty to weather variability. And then you can see the CGAP post-process output. And this is the current setup we have and what it actually looks like. And so I'll start off now by talking about our actual cloud optimized infrastructure that we've set up. Before coming into this project, I didn't really know how hard it would be. And it's actually not so hard. We've had lots of help, especially from the impact. But it's been a lot of very technical development of how exactly can you do this? How can you make it very optimized, efficient, so they can really use it and use it to the best possible way. So in the cloud optimized AI systems, there's several parts. You can see that we start off with having our forecast that we want to train an AI model so that we can post-process it to deliver improved, accurate rainfall forecasts. So that's the second part. How do we actually train that model given that we've got all this information? And we want to do it in a way that's optimized to the cloud. And then, of course, we want to train our model, and then we have a model. So the first part, you've got the forecast output. This is like very, let's say, multi-dimensional data. So you've got multiple variables, each of them having longitude, latitude, time. So it's a very high dimensional space. And for that, we really try and follow analysis-ready cloud optimized data protocols. So this is something that's just been developed overall in the cloud computing community, and it's heavily emphasized. The analysis-ready data means that it's a meaningful, complete data set. And also it's community maintained or has some proper curation going on so that everyone trusts it, people use it, and we can also exchange information and follow fair concepts where it's findable, accessible, reusable, and interoperable. And of course, then we can also reproduce data from different groups, and that's very important. The second part is cloud optimized data. So as I said, we've got this really high dimensional space where you've got lots of different dimensions with which you have to work with, you have to section with. The idea is it's a very large monolithic file, and you don't really want to load it in because that would be petabytes of data almost. So instead, we use chunking, where you can efficiently slice and select the data. And in that way, the data itself has to be stored in an optimized format that you can just chunk the stuff that you want to access without having to load the single monolithic file. That format that we're using is called ZAR, and it's been widely used, but there is a paper out there that talks about it and exactly why it's so important. And the nice thing about ZAR is also there's a lot of data that's stored in what we call GRIB format, and there is an easy translation between GRIB and ZAR. So all the forecast output that is already out there on Cloud Bucket, we can access through this. And that's actually already massively. So just to elaborate on what ZAR does, in a very layman's way, it's just basically a massive directory of individual files. So it stores multiple individual files instead of a single monolithic file. And that means that each file can be referenced, and this is very important. Each file can be referenced using an externally stable path. And that is a very important thing because it makes it highly scalable for cloud storage. So in cloud storage, you have a certain HTTP file protocol storage system. And with this ZAR format, you can basically just create metadata that references these files on the cloud, and you can just scale up your cloud storage, which was a massive leap, at least in my eyes. So that's the cloud-based data part. And now I'll move on to how do we actually access this data and then feed it into the model in a way that the model isn't overwhelmed, and in a way that we also don't have too much latency between bucket and the model. For that, what we do is we use a lazy loading method, which is that we only call the data when it's required. So for people who don't really understand what this means, I would say it's just streaming. So you're just streaming data into your AI model, which is pretty cool, I guess. And we use something called X-Batcher, which means that you can have on-the-fly slicing and organizing. So you on-the-fly slice your batches and can then stream them into your model. So you're basically just streaming data into your model from the cloud with no download needed. And this X-Batcher has been developed by people over at Carbon Plan and Earthmoon. We're also in contact and would like to see some GPU benchmarking tests, especially for operational usage of this kind of stuff. And then, of course, this would be the whole setup. And the idea would be that you just have cloud-based data that you can then efficiently slice and feed into your model. To juxtapose the two, so the usual approach to what I just presented, the usual approach really means that you need to download your data. And that's a lot of data to download, especially for training a model, and it takes a lot of time. For the X-Batcher approach, we don't really need it. The usual approach also needs you to sort of prepare your data. So that's in a TF records format. That is something that the machine learning models usually need. So depending on the package you're using, you need a TF records or some other readable format. The X-Batcher doesn't necessarily need that because all you have to do is create some metadata that references your file systems on the cloud. So that preparation itself is very little time. The data setup, usually when you then have to load the data and feed it in, is a bit longer for the X-Batcher than the usual approach. And that's mainly because you're initializing the model so that you can start slicing it and you're trying to understand the data format. But that's minutes, and compared to the other two things, I think it's quite trivial. And then the training time is the same. So there's not really that much latency between retrieval of the data and feeding it into the model. And these results are based on a dry run that we did on the Google Cloud using an NVIDIA L4 GPU. So it was pretty fun to do and pretty exciting to see these results that we can actually start streaming data into an AI model for operational forecasts. So now I'll talk about the comparison with other models. And there are two other models that you can get rainfall forecasts for. The first one is developed by Google, GraphCast, and the second one is Foxy. Both of them are deterministic and global forecasting models. So to juxtapose that to the CGAN that I presented in the third slide, the CGAN itself is a probabilistic one, so it's not deterministic. It gives you a range of uncertainty, and it's a region-specific one, so it's for the Greater Horn of Africa, whereas these two are global and deterministic. GraphCast is based off a graph neural network, which is encoder processing decoder system. Oh, what's that down there? Can you read French or?
Press a key number.
That was not part of the presentation. Yeah. Okay. And FOOXI is a cascade model. And I'll just briefly explain what the difference is, or what you guys should know about what the difference is by looking down there. So both of them are trained on error fiber analysis, which again, I would like to emphasize that CGAN is trained on actual observations on the ground, whereas analysis, and this will also come out in a bit of why that makes a difference. But both of them roll out the forecast. So that means that they iteratively predict on their previous state. So they get an initial weather state, and then they predict, and then they predict on that prediction and iteratively repeat so that they can roll it out and get a forecast out in 2 weeks. And what that means is also that they've got accumulation of errors. This is a typical problem that you get in weather forecasting with AI. And FOOXI and GraphCast have two different methods of dealing with that. FOOXI is based on a cascade model, so it optimizes for short, medium, and long-term range forecasts. And so it sort of optimizes for 3 different models, if you want to think about it like that. And fits very well in terms of errors, but that might also mean that it's a bit too strict on itself and can't predict the extreme. So it sort of regresses to the mean and it's quite smooth. And GraphCast, on the other hand, doesn't do that. So it first just does training. And then after that, it follows a curriculum routine where it fine-tunes its parameters based on incremental or regressive steps. And that's just the difference. And again, the CGAN that I presented, that's part of our project, doesn't need to do this because we just take the forecast output and post-process it. So it's a hybrid approach. Great. So here's an intercomparison of the model, and this is the mean absolute error compared to iMerge satellite data for rainfall in millimeters per hour. You can see going from left to right, GraphCast, FOOXI, and CGAN. I do have to emphasize that this is on a test period, so not the training data that the model knows, but out of sample data. For GraphCast and FOOXI, that's 2023, because they were trained on 2021 and 2020. For CGAN, that's 2020, because it was trained on 2018 and 2019. So it's a bit difficult to really compare, I would say, because different years have different variability. But overall, you do see that GraphCast and FOOXI have more errors towards the mountainous regions. So towards the Rwenzori, so if you go towards Tanzania, and then also Ethiopia, and also Mount Kenya, you can see that overall. All of them seem to show high errors, and that is Lake Victoria over there. So that's a very unique climate system, which has been a project for lots of people from the age-old time, and it's extremely difficult to predict, and none of the models can either. If you look at the error 5 reanalysis errors compared to iMerge observational data, you see that they match quite closely to the GraphCast and FOOXI errors. So we can sort of see where the errors are coming from in relation to the on-the-ground observations. So yeah, that was quite an interesting finding. Now I want to make it a bit more concrete. So I'll talk about what happened in April. So I guess that's last month. Last month this year. It was really rainy over Nairobi, over Kenya. You can see that there was a lot of flooding. This is actually a picture my dad sent me, and it's Waiyaki Way, just like down the road from our house. It was flooded. And here is an intercomparison of how the models performed for that time period. So this is the difference between the actual model prediction and the iMerge satellite observations for that time period. And I'm picking 22nd to 28th of April because that was just really, really rainy. I wouldn't really rush to any conclusions from this, but it's just to show how the models performed compared to what was happening and give a wide range of selections. So you can see GraphCast, FOOXI, CGAN, and blue means that there is a underestimation, red means overestimation. information. And you can see generally, so Nairobi's right here, yeah, where there's a lot of rainfall, and you can see there's also significant underestimation. So a lot of the models can't seem to capture the extreme rainfall. This is a well-known problem across models though, and it comes from the fact that they're optimized for root mean squared error. So it's safer to predict something that's closer to the mean than dare to predict something closer to the extreme. So we're not too surprised with these results, but it's interesting to see that it's present across all the models. Now coming to the communication part. We have a user-friendly web-based platform. I would encourage everyone who's interested to visit it if they like. And it gives the output of not just the IFS data, but the post-processed CGAN data in real time. So initialized every day, it gives the forecast for the next day over 24 hours. And people have been using it. You can, go to, and we're also working on setting it up. So I'll talk a bit about the communication side of how exactly we're trying to also visualize data so that on the ground stakeholders can actually make the most optimal use of it. But coming to some of the questions I think that were asked at the start of this session, this is a user-friendly platform that's online. During the floods that happened, that I showed 22nd to 28th of April, all the Met bodies were really inundated. There were so many requests. They were completely burnt out. And presence of this kind of website would really help inform people who can't really get access to that data because there's too many people asking for it. And also the cloud-based infrastructure means it's hosted in a stable platform that is also not too dependent on the on-the-ground infrastructure. So that's honestly a massive leap towards increasing resilience in accessibility of disaster information. Here are the results for, sorry, it should be 22nd to 28th of April, but we did a comparison of actually what the performance was for the IFS forecast output, the post-processed CGAN output. And here you can see the actual results. So the CGAN output, the IFS, here we take the mean over the ensemble, and you can see what it was actually like according to the image data at the bottom. You can again see that there was a lot of rainfall over Nairobi. So here, and this was actually one of the main impact areas. And you can see both IFS and the CGAN captured it. More importantly, towards the far left, you can see the difference in performance. So we calculated what's called the continuous rank probability score. So it's a probabilistic measure of the mean absolute error, and it's a proper scoring technique, meaning that it's most likely to actually not be biased, and if you give it the actual observation of data, it will always rank that, or hopefully always rank that as the best fit for observed data. And we look at the difference between that score for CGAN and IFS. So here you can see that blue means that the CGAN, our AI model, performs better, and red. And this really contextualizes the added benefit of the AI model. You've got this cloud optimized platform that people can access through the website. And you can also see that it actually gives a better skill score over the affected heavy rain area. So I hope that really drives home the potential of AI-based cloud optimized approaches for forecasting. Another just more for fun, communication thing that we did is that there's the Greater Horn of Africa Climate Outlook Forums that we also take part in and really emphasize taking part in along with project partners from ICPAC. And we try and also explain different concepts like probability, because they still use a lot of deterministic forecasts and it's difficult to actually communicate probability to the on-the-ground people. This is a prototype of probability plots we're trying to make for them, based on also this Nature paper from colleagues at ETH in Zurich. And I thought I would showcase it here, but of course, the idea is that if they don't like it, we won't show it. But this is a prototype that we've been also trying to co-produce with them. So that's also part of the project of how do we best communicate the information. And this is just an example of what we've done and how we're trying to co-produce information so that it's the most meaningful for them to put out. So the probability plot itself looks at the maximum rainfall over this little red square, sorry. And it looks at the climatology for April over this red square and what the maximum rainfall is
over all the years of 2018 to 2023. So every day of April 2018 to 2023, we just look at the max rainfall in this thing. And then we can divide it into bins and see what the counts are for each bin, going from 0 to 20 millimeters per day, 20 to 50, and so on to 100. And then we can just extract what percentage of each bin count exists and plot it in this way that we're hoping is a bit more intuitive for people who don't necessarily have a strong statistics background. So for example, here you can come to the conclusion that for more than 70 millimeters accumulated rainfall, there is a 2 out of 100 chance. So each dot represents the count of the bin. And you can see that there's 100 dots, and then there is a 2 out of 100 chance of picking this up. Yeah. Rainfall. What's important is that it really shows the increased chances when there is a heavy rain period. So here you can see we show the ensemble forecast, and then you can see that there are much more orange, yellow, green dots over the case study period that I showed, so 22nd to 28th of April. This is, of course, a prototype. So we're working on co-producing this with the people at the region, but if they don't like it, then we won't use it. And so it's just more of an example of how we're actually trying to interact and also have this more inclusive way of getting information out there as quick as possible, as meaningful as possible, as understandable as possible. So thank you. Please do visit the website. There's this massive QR code you can scan. Otherwise, there is the URL at the bottom. And contact me if you guys have any questions or any collaboration ideas. We are always open. Yeah.
Great, very nice overview also from. So yeah, we have 1, 2, 3, 4 questions, and I think that them goes also. Yes. Thanks.
Okay, thank you very much. That was super interesting. I was interested in how you're using that data to inform anticipatory actions and kind of what sort of the window of opportunity that it's able to give people on the ground who are then implementing those actions.
Yeah, good question. So we work with the World Food Programme, but something that we really emphasize is that anticipatory action and early warning systems is a very inclusive approach where we need to also engage the local people and more so give them more, let's say, agency in doing it. So a lot of the anticipatory action is mandated through them and they have to make the decision. So ICPAC is the main sort of leader on that. And we only try to give them the information, but they know best what to do because they have the best communication with on-the-ground stakeholders and municipalities, for example. There's also other synergies that we do have. For example, there's this inflow project with Red Cross, and they're working with improving the flood modeling. So rainfall and more accurate rainfall would be really important for them. But we emphasize just having the information and making sure we can deliver it to the local people who know best what to do with it. And we really try and stick to that.
Yeah. Quick technical comment, the ERA5 forecast data is actually not a reanalysis, it's a short-term forecast.
No, we're using the GraphCast and Fuxi are trained on the ERA5 reanalysis.
Right, and the ERA5 reanalysis forecast data is not a reanalysis, it's a short-term forecast. Technically, we can talk about it afterwards.
We can talk about it later, but
my question is, why didn't you use GraphCast as a model? So what's the advantage of actually using ZGAN, with spoken ZGAN compared to just using GraphCast or Fuxi?
So the way that this was planned was that we wanted to take the IFS output, the forecast output, and explore the potential of post-processing and hybrid approaches. This was also based off some other work that was done at Oxford over the UK, where we saw that there was some promise. And also, furthermore, we could potentially do more downscaling, which we're still trying to explore. So the idea is that, of course, GraphCast is good, but it's trained on ERA5 reanalysis or reanalysis forecast, whatever you'd like to call it. Obviously, that doesn't match the observations. So we wanted to have something that was much more trustworthy, that the people on the ground actually wanted. And that was what they wanted.
I think you probably mentioned that one could fine-tune GraphCast further.
Yeah. So you could fine tune GraphCast further. And so we're not really making it a competition. So we've also got Fuxi, and in the end, we would like to have as many models as possible. So for example, we also don't just want to post-process IFS, but we'd also like to post-process GFS data from from the NASA, so not from ECMWF, and see which ones are performing better where. And then the idea is that if we can just give this information, compare them, build some trust in the models, then the people on the ground could choose which ones that they want.
Yeah. Thank you for better presentation. Just I have some questions regarding on how you measure your accuracy and how you are trustworthy. Because, like for instance, likely you have applied this in Africa. Like, let me take a case study for my country. Sometimes crowd looks like generating lane, but unfortunately, lane cannot be appeared. So, how you trust your accuracy and how you measure that accuracy, kind of like that.
Yeah, so I mean, that's a really interesting question because that's again, like, we can always use these scores like mean absolute error and CRPS. But for example, the local forecasters really just want to look at the difference between the predictions and the observations. And that's what they want. Or for example, you can have what you think an accurate forecast, but it could just be off slightly. So the heavy rain could be just slightly in a different area, which is a bit more mountainous, and then you've got a different sort of impact. So we are really just trying to work with, again, with the ICPAC and the people who have more experience in delivering forecasts and also measuring their accuracy. We are trying to move a bit more towards proper scoring, so the CRPS and ensemble-based accuracy metrics. But yeah, it's something that I think is, again, like a work in continuous progress.
All right, thank you, and welcome for just this project is better and come to apply this in Rwanda because it's might be very.
Yeah, we'd love to apply it in Rwanda. I think we've been in talks with people over at Uganda.
Okay.
And I mean, Rwanda is part of the ICPAC. So you guys still actually have access to these forecasts if you want.
Thank you.
Do we have one more?
Yeah, sure. So earlier you were showing kind of like the errors between like Foxy and GraphCast and your own model. And then I think like, I don't know if I missed that, but did you say that you're trying to also separately predict what the errors will be with a separate model? Or is that something that you haven't done yet? Because I know like Google for their flood models, one thing that they've done like recently when they've tried to improve the performance is they have a separate model that's using like the exact same predictor information, but instead of predicting the like output, it tries to predict what the model error would be. Like it's predicting like whether it's underestimating or overestimating like stream flow and by how much. And then they can then feed back that into like their model as like a new predictor essentially. And then it can be used by the model to kind of like overcorrect. So I was wondering, like, I couldn't see, like, is that what you're doing or is that something that like you're considering? Does that make sense?
So, well, the slide that I showed with the errors was just to show how the models compare with one another and contrast them. So this is just more like a performance slide. I'm not aware of Google or Fuxi planning to do this. So, I mean, if they want to, they can obviously, and then we'd also think about doing it in Zigan, but that's not been on our radar so far. I'd be interested in hearing a bit more about it, but
I think that method tends to work well when you have like specific areas that are like consistently over like underestimated or like specific conditions.
I mean, the problem here is that I think a lot of the overestimation over the mountains is really just coming from the fact that it's trained on error 5 data. So that also might be a problem. I mean, there's also the problem that we know that iMerge data itself underestimates the rainfall amount. So the data that we had over the extreme rainfall period in April was still underestimating what we actually observed in the rain gauges, which was up to 100 millimeters of rain. So I think, at least for us, like the first most important thing is to get access to better data that also has a lens towards getting more extremes. So I know people in Rwanda have a radar actually that it might be operational. So we're trying to also get our hands on that radar data and then see if we can actually get a better data set. And then of course we could start thinking about the errors and feeding that in, but we need better data in the first place, I'd say. Yeah.
So thanks again. The last discussion really showed how complex kind of this problem is to solve the early warning, to address the whole early warning chain. And yeah, I think we should keep on thinking about it and take action as well. So with this, basically, let us close the session. Let us actually thank the speakers and thank you for the participation. I think that was a productive discussion. So I enjoyed it a lot, and again, we should keep in touch. Thank you.